You see, up until the 1990s, the internet was this shadowy little researchy experiment predominantly driven by US defense money with a few in-players. And the real scene in networking, the big thing, for private networks, it was the vendors, IBM's SNA architecture, we discussed DECnet, Wang, and so on. And for the real players, the people with hairs on their chest, because they were networking men, were employed by telephone companies. And they were going to inherit the future. And they were working on this ornate model called the Open Systems Interconnect Framework. Now, I think it's pretty clear, and we've had not just decades, but probably centuries of experience, that if you really want to stuff something up, if you really want to take the kernel of a good idea and trash it and turn it into unmanageable soup, destroy it, hand it to a committee.
You're listening to Ping, a podcast by APNIC discussing all things related to measuring the internet. I'm your host, George Michelson. This time, I'm talking to Geoff Huston from APNIC Labs again, in his regular monthly spot on Ping. Geoff and I discussed 240/4, the last significant block of undelegated addresses remaining in IANA's control from the IPv4 address field. Why is such a large tranche of IPv4 address held back from use? Geoff and I talk about the original classful model of addressing and the implications of code from decades back with a vital bit mask test on the upper 4 bits of the address field. 240/4 tickles the Class E experimental not for use filter, which may have been removed from current BSD and Linux kernels, but persists at large in the field in millions of devices. Geoff has been measuring using the APNIC Labs advertising system to test reachability to 240/4. His evidence suggests there's a long road ahead to make this address space usable in the wide.
Welcome to Ping. What shall we talk about this time?
George, it's good to be here. Both you and I and Ping are actually hosted in a regional internet address registry.
We are. And our stock in trade is actually IP addresses. And so today I'd actually like to talk about IP addresses. Oh, and work. You want to talk work.
Good point.
Okay.
I want to talk about some of the anomalies that have appeared and some work I've been doing about finding some IPv4 addresses in a dark, dusty and unused cupboard and sort of seeing what it meant, okay?
All right, so we're talking about the bottom of the barrel.
Well, we are, but let's talk about the barrel first. And let's actually talk about the IP protocol. And for that, we kind of have to wind back to 1968-69, the first iterations of packet-based networking. And at the time, you might recall, or you might be a bit young, I know I am.
I'm younger than you, so my mind was on other things, train spotting, amongst many other bad habits.
There you go. And computers on your wrist were in the realm of Dick Tracy. A computer at that time, early 70s, was a big beastie, a very big beastie, because integrated circuits were recent, everything was large and discrete transistors, computers weighed tons, you needed lots of air conditioning, special rooms, cost millions of bucks and had about, 5 bytes of memory.
So over my shoulder, that the listeners can't see, but you can, Geoff, is the memory board from a DEC 10 mainframe that I pillaged of that vintage in all its glory. They brought French lace makers over to DEC's headquarters in order to teach them how to wire up the core magnets in the plane. Anyway, continue.
I'm stunned by that. I have an asynchronous I/O card from not the same DEC 10, but a similar vintage DEC 10. But anyway, I suppose where I'm heading was there weren't many computers. And when they started to think about connecting them together, the first idea was to connect the central computer to a bunch of what we called peripherals, which was basically card readers, printers, and if you were rich enough, your own electronic glass terminal. And, anyone who owned one of these didn't have millions and millions of these peripherals. They had a tiny number.
50, 60, maybe 60. A couple of hundred max.
Well, all that fits in 8 bits.
If you have to assign them numbers to say which one you're talking to, yeah, totally. You could say number 25, you could say number 255. You need 8 bits to say which numbered peripheral are you talking to.
Well, we're talking digital networks. So, yes, they all had numbers. And the first of these kind of early efforts at networking that needed to address devices, realistically did 8-bit addressing. But then sort of things got a bit commercial, still mainframes, still peripherals. But then there was this sort of emerging concept that not only could you connect a mainframe to its peripherals, you could connect mainframes to each other. Aha. And the numbers started to balloon out. And so around the 70s, we'd gone from 8-bit networking, 256 max, to 16-bit networking, where the address field was a phenomenal 16 bits long. Now, if you were numbering everything from, 1, 2, 3, 4, 5, you get up to 65,336 or 335 before you run out of 16-bit numbers.
And that is a hell of a lot more than the number of addressable units on anyone's radar in the immediate present condition. There were not that many computers in the free Western community to be connected together.
Ever. And so considering the kind of richness of computers, i.e. very few, but this phenomenal 16 bits of addresses, what they actually did was something quite clever. They divided the address into 2 parts. And in DECnet terminology, it was area number and node number. Other networks, SNA, WangNet, I love that name, BurrowsNet and so on, used slightly different structure. But the whole idea was you had this internal structure of addresses where you could connect multiple computer centers together. God knows how. Maybe you shouted at each other. And each of them would be assigned a new area kind of number, and then that number within that. So all the computers on a campus shared that same kind of node or mainframe number.
Yeah. If you looked at the X25 network that was emerging in Europe and the UK, Janet, for instance, they had a larger number field, although it was measured in octets, which were highly inefficient. It was not a byte-efficient networking structure, and you gave a campus 2 octets worth of address space as subnets, but you were using effectively binary coded decimal. So you had 100 local stations in a uni, and you had all the rest of the address bits basically not doing very much because they were for some central authority to manage. You didn't have anything like as much freedom to address as you got from things like DECnet.
Well, the big dreams of the telephone operators. But I actually want to press down the area of packet networking because it was around this area, 1974, that the first of the sort of revolutions in the internet came across, and they started doing the early incarnation of this IP address architecture. And they settled to a 32-bit address. Now, 16 bits is a lot. We said in the 70s there were, more addresses than computers that existed by orders of magnitude. Well, 32 bits is 4 billion.
Yeah.
No right-thinking humanoid could ever imagine a universe that ever had 4 billion computers. The surface of the Earth would be covered in computer rooms.
We'd have to be carrying computers with us all the time if we were going to be doing this. Unimaginable.
Right, so this was an amazing dream. But nevertheless, they pressed on, despite some trenchant opposition at the time, and said, we're going to use a 32-bit architecture. But obviously, it's not going to be flat. We're going to put in a structure.
Yeah.
And in 1974-75, you actually see the first incarnation of this structure And each site, each sort of component network of this internet network, each component network was given an 8-bit identifier. And because it was a 32-bit field, the remaining 24 bits, you could go crazy all on your little lonesome. Up to 16.7 million peripherals, whatever you wanted to number, but, do what you want. So it was a simple structure of an 8-bit sort of area code and a 24-bit computer code identifying the computer.
Yeah. But that carries the seeds of its own destruction really quickly, Geoff. I mean, Blind Freddy, looking at the universe of entities, even just in America, that want to engage with ARPA in a nascent ARPANET. Well, there's more than 255 of them. There's 50 states. They've each got a uni. There's the beltway of companies that supply service. There's the government departments. 255 things, each of them allocating 16 million addresses, is not a terribly good fit.
Now, at the time, no one was trying to network the world with this technology. So in some ways, they still thought of this as a little experiment being conducted predominantly with the Defence Research Agency, ARPA, or variously DARPA's money. And so it was more of a proving ground. But even so, you're right. This only accommodated, at most, 255 players. And as things were turning out, there were more than 255, entities expressing interest.
Yeah. So they had to modify this model.
They had to modify this model. And the first documentation I can find about, how are we going to structure this to make things work, is actually an RFC 790 from September 1981.
Right.
And this was the first time, instead of having just one structure, they had 4.
Yep.
Half of the network address space, which had the numbers that started in the first octet from 0, in fact, 10 was reserved, all the way up to 127. 127 was reserved, were going to be used for big networks.
These ones that you've talked about, the 16 million big subnet networks.
Or to tell you the truth, what they did was just inherit everything they'd done.
Yeah, which luckily lay inside that space.
They'd only had 44 co-travelers. So, if you look at RFC 790, you'll see BBN packet radio, SF packet radio network. The British Post Office got network 15.
Yeah. The Ministry of Defence got a network. I mean, there were kind of early players. Digital Equipment got a network.
I'm trying to find them down there, but yes, because the list is published. It's kind of the very, very early players.
Yeah.
Interestingly, UCL, the University College of London, got two.
Yep.
32 and 33.
Yep.
What were they thinking?
Well, one of them went to the MOD in Goonhilly Downs. So I'm coming into this story in about 3 years' time, Geoff. Keep going.
All right, yes. So Digital and DECnet got number 37. But now you see they had the other half of the address space, 2.3 billion addresses, that they could play games with. So again, they took this address space, 31 bits, and again sliced it in half.
Yeah.
And so the low part of this, they called the Class B networks. And instead of using 8 bits, they used 16. So you had 16 bits of, if you will, network identifier and 16 bits of host identifier. So these were for networks which were not as big as the ones that were, envisaged in the first class, Class A, but, they were still of some size, campus network, etc. In 1981, because it seems, I think this system had only just started, it records that zero of these Class Bs were actually assigned to anyone. So that's what leads me to believe the first 44 was the only 44 that had been allocated.
Yep. Now, how many of these could there be in the entire internet if they followed this rigid model?
Well, again, 16 bits worth 65,500 and whatever it is. 65535.
Looking at the surface of people who were playing in connected networks around this time, there was America, and there was Canada, and there was Britain, and there were economies in Western Europe, and there was probably people in Australia poking their heads above and people in Japan poking their noses over the realm, maybe one or two in China. 65,000 is a pretty good fit for the number of tertiary education and research entities that you thought probably could put their hands up to get some of this.
Well, research experiment. No one ever dreamt that big, but they were trying sort of these concepts. So they thought, well, we obviously need structure, and so we're going to use a 3-part structure. So the first one was actually big. The second one was medium, class B. And the third one, which took the remaining 30 bits and again divided it in half and had what they call class C networks. And this had 24 bits of network identifier, allowing for approximately 17 million, but it won't be that many, and only 8 bits of host identity. So this allowed for a phenomenal number of small networks that had at most 256 computers in them. Don't forget.
Gosh, small, 256 computers. Most places only have 2. This is more than enough.
Even the personal computer was merely a pipe dream.
Yeah.
Don't forget, 1981, we're still banging rocks together pretty badly. Computers are big things, not tiny things. So, I'm going to wear a computer on my wrist. You're joking. Unassigned, all of them. So, oddly enough, that left a bunch of addresses up the top.
Because you've done half and then half of half and then half of half of half, and you've got this last fragment left.
Half of the last. And 224 through to 255, they just said reserved.
Yeah, we'll think about that later.
And it was RFC 790. And the issue was they kind of felt they'd kind of done the Goldilocks division. They'd, made something big, made something medium, made a lot of small things, and, they were set to keep on running. And that stayed there for an awfully long time. Until Steve Deering, who actually ended up doing a lot of the major lifting for IPv6, before he did that, he did his PhD at, and I'm going to take a guess, and Steve can poke his hand up, he's still alive if I'm wrong, I think it was Stanford. And it was on this weird technique called multicast. Now, multicast is odd because what it does is it tries to replicate a packet to every member of that address family. So it's a bit like broadcast in TV land, but you don't need to be close to the antenna. You just need to be dialed to the right frequency. And what that means is you need to have the same address as the rest of your multicast group.
It's an overlay network model when we come down to it, because to get to all these disparate elements, you have to implement tunnels over a fabric and glue things together and have people telling each other they're members of multicast groups. You're not there all the time. You kind of have to register and deregister a bit. But it heads to a place where if you were doing something like a broadcast, you could send one copy of it from Brisbane to Canberra and then have 50 or 100 or 200
or 1,000
or 2,000 people watching it in Canberra and only send one copy.
Now, these were brave and adventurous people. They're also bloody crazy. They didn't use tunnels or anything easy like that. They actually did it in the routers. And so you had to deploy multicast-aware routers, and the packet replication was happening all the way down there in the router. Weird stuff. And oddly enough, there are still networks. I think Japan runs one where they use internet television using multicast simultaneous. It's basically is television. Everyone sees the same thing. And the way you do that is by multicasting the video stream. So it's not completely outlandish, and folk do use it, but they needed a special class of addresses. And the routers needed to rapidly know that this address needs weird packet handling. You need to keep a table locally of all the interfaces that are part of that multicast group. And when you get an incoming packet with the destination of that wacko address, you have to replicate it and send it out all the interfaces that are mapped from that address. Broadcast was so much easier. Just stand on a hill and shout, No, multicast was go through convoluted loops. So they needed addresses. Oh, we have this 1/8 of the network. Let's divide it in half. And now let's create a new class of addresses, class D.
Yep.
Cool.
A's the biggies, B's the mediums, C's the small, D the weird multicast. But
D was the first weird idea.
But we don't know what we're going to do with the rest. So we won't use all of the remainder. We'll carve it in half and use the front bit of it for the D's.
And the rest, which we will call class E because we were doing fine with the alphabet, we will just stash them aside and we'll call them for future use.
So we've got 0 up the front. Nobody's able to use that.
Yeah.
We've got 127 in the middle. Everybody's able to use that, but it never leaves your own computer. It's the local loopback. We've got
it's the identity loopback.
We've got a scattering of blocks that we put into this magic private addressing bucket, but they fit the general model. There's a big E, a medium E, and a little e. And we've got weirdo addresses up the end that we use for this sort of broadcasting, but it isn't. And then we've got a leftover bucket we're going to call class E. It's future use.
Future use. No one should ever be using it, should they?
So what time frame have we come to, Geoff, with this decision?
Oh, multicast kind of hit the streets in 89, 90. There was all these working groups in the IETF of DVMRP, SGRP. There was the whole mythology around multicast. Because it was
we probably have people listening to this podcast who weren't even born yet. And we're talking about some rules for addresses that left a bunch at the end called Class E saying, yeah, we're not using these, that's for later. More than 30 years ago.
Well, if you put it like that, yes. So there are a lot.
A lot.
It's a /4. And what that means is there are 268 million. To be precise, for those who really worry about numbers, 268,435,455 of these addresses, which start with 1, 1, 1, 1 in a binary form.
Right. And a biggie in the old model is 16 million addresses. So this is like somewhere between 10 and 15 biggies, all available, all unused. Now, one of these big blocks is a phenomenally useful amount of address. 16 million addressable things people lust after. This is an Amazon scale thing or an Alibaba scale thing or an entire economy scale thing.
It's a big number, 268 million.
That's a lot of addresses to be left unused at the bottom of the barrel because we just didn't quite get around to working out what to do with them.
You see, then comes in the law of unintended consequences, because around the same time, actually, as multicast and everything else, there was a shift in thinking, firstly from the Americans, but then from everybody else. You see, up until the 1990s, the internet was this shadowy little researchy experiment, predominantly driven by US defense money, with a few in-players. And the real scene in networking, the big thing, for private networks, it was the vendors, IBM's SNA architecture. We discussed DECnet, Wang, and so on. And for the real players, the people with hairs on their chest, because they were networking men, were employed by telephone companies, and they were going to inherit the future. And they were working on this ornate model called the Open Systems Interconnect Framework. Now, I think it's pretty clear, and we've had not just decades, but probably centuries of experience, that if you really want to stuff something up, if you really want to take the kernel of a good idea and trash it and turn it into unmanageable soup, destroy it, hand it to a committee.
Have I been on these committees? Have you been on these committees?
Hand it to a committee.
Yeah.
And the thing about OSI was that it was the telephone industry in all of its wonderful diversity meeting the computing industry in a committee.
Yeah.
The same kind of cross attitude that led to the ATM framing protocol, not using 32 bytes and not using 64 bytes, but splitting the difference, coming up with 48, and then adding another 7, or no, adding another 5 because they could. 53-byte cells. Riddle me that.
So I'm going to take a small amount of time here, a really small amount of time, to kind of stand up for the OSI side and point out
I'll run away.
That we are really only just saying the road not taken. We could have elected to go into line with this. And in past pings, we've discussed how it could have been a rational decision to adopt some of the aspects of the telephone model. We could have done address distribution in a prefix-based manner. We could have done routing in a model that aligned to that. We could have been in a different world. We're not there, and no amount of dreaming is going to get us back there. It really was just a decision that was made that has some irrevocable consequences. Getting into better, worse, I don't think that's useful. The point was it was a committee of two cultures that just were very different to each other.
They were
and what
very
came
different.
out the door was a choice that was not aligned to that model. It was a different view.
The telephone guys loved connection-oriented transports, virtual circuits. They'd come from X25. So there was a connection-oriented profile of OSI.
Yeah.
Another group of folk, predominantly computing folk, came from data networking. They had experience on Ethernet. What's this circuit nonsense?
Yeah, we don't do circuits.
Don't do circuits. So the committee said, can't reconcile. Let's do both.
Yeah.
And then someone said, how can you bridge them together? And the answer is, you don't. You just can't.
Yeah, it's funny how some things, though, re-emerge from this model. For instance, the aeronautics networking people looked at switches that are based on preemptive jamming of signal and said, wow, airplanes really don't like this. How about we take all that hardware and say, let's only ever talk in it using time division muxing? And they basically took Ethernet switches and re-specified them from airplanes as you get a cell slot at a fixed time, but you are guaranteed that bandwidth to send your signals. They took the technology and they re-implemented time division multiplexing on it. You know, okay, rational choice for an airplane.
Still around. I'm on a passive optical network for my access fiber to the home. Guess what the return channel is? I've got to share it with about 32 others in theory. Time division multiplexing.
Yeah, so these things kind of come back together again. But yeah, it was religious warfare in the trenches.
Where I'm leading to, where we're leading to, this long diversion, there was an attitudinal change.
Yeah.
Because when confronted with OSI, the response, particularly from the nascent internet protocol community and from the computing industry, which was gathering heft, was, no, not going to go OSI. The internet is real and the internet is where it's at. All of a sudden, no longer an experiment, no longer, well, we're all going to, the adults will come into the room, we'll pack up and go home. They'll thank us for all of our experimental work and go and do something better. The answer was, you're stuck with it. Now, some of you could remember being able to cast your mind back to 90, 91, 92, 93. The landscape had personal computers and they were getting smaller.
Yeah.
The landscape had early Apples getting smaller. The landscape started to have some wacko stuff by Nokia and the Japanese, Docomo, of putting IP protocols on phones. There was this glimmer that said, if you're everything in the computing industry and everything in the communications industry, things are going to get pretty weirdly big, pretty bloody quickly.
Yeah. These assumptions about fitting in the Goldilocks A, B's and C's is just not going to work. We have to encompass a different model of use. We need to think about finer-grained approaches to managing this stuff.
So Frank Zelensky had appeared at an IETF in about 1991 and said, guys, you're going through B's like crazy. And I do say guys because there are very few gals around at the time, which is terribly sexist at the time, but that was just a different world. We're running out of B's. We've got about 3 years to go. What?
Yeah.
C's are fine.
Scary.
A's are fine because no one's big enough, but, B's have only 8 years to go. And all of a sudden, the idea that we were going to take over the world of communications with all these computers, but we wouldn't have addresses to run them was kind of, oh my God. So panic, absolute panic. We're going to run out. In all the panic, there were two answers, the short-term patch and the long-term fix. Short-term patch, why don't we allow variable length network addresses? So instead of having only 8, only 16, or only 24, depending on whether you've got, 270 hosts or 400 hosts or something, we can tailor the size of the network prefix. It was called classless addressing. CIDR because the place we implemented it was in interdomain routing, IDR. So the key technology was classless interdomain routing.
Right, because the things we called A's, B's, C's, D's here were called Class A, Class B, Class C. So classless meant not aligned to those classes. It's a different model.
Right, and part of the issue was B's were actually a bit too big and C's were a bit too small. And so instead of either having 8 bits or 16 bits, I want 12. I want 9. I want 10. I want a sort of a space that has fewer hosts than a B, but more hosts than a C. Now, oddly enough, we thought, oh yeah, that'll serve a few years. And so we can work on the real answer. What's the real answer? We went from 16 to 32. So if we're going to be logical, let's go from 32 to 64 bits.
Yes. More.
Oh, what a big number.
More.
Up the quintillion. But we were starting to dream very, very big. And looking back in retrospect, I'm not sure whether we were on drugs or not, but oh my God, we decided not to go 64 bits. We decided to double up again and go to a phenomenal 128 bits.
Yeah, push the problem out into a horizon that it felt like it would last significantly longer than the jump from 16 to 32 had last. I mean, the jump from 16 to 32 bought 20 years.
Yeah.
But the longer term is trying to buy 256 years, unimaginably more time by going to an unimaginably bigger address. Oh, how simple we were.
Oh, there was this website around about very, very big numbers. How many ants exist on the Earth? If you took a grain of sand and wanted to build a new Earth, how many grains would you need? Big numbers. Turns out the 2 to the power 128 is bigger than all of these big numbers. It's a very, very big number.
Yeah.
And in some ways it was overkill. But the whole idea was, and again, I'm going to reproduce the thinking of the mid-90s, running out of addresses for an address-based network was a disaster. So the only thing we thought we could do was do a stopgap because we weren't really running out of addresses. We were running out of Class Bs. So let's make it classless so we don't run out of Class Bs. We're still going to run out. So let's jump from 32 bits to 128 bits before we run out. And then this problem will be solved for lifetimes. There just isn't enough silicon, in order to stress out this model. We're done. We're over. We're finished. Right? So if we play this through, what happened in 2010? Because by then we'd actually got mobile phones.
So you're compressing a little bit of history here that we probably could touch on, which is that there was an experiment and people tried moving the boundary around to prove that it worked, and a whole bunch of technology shifts got done to get rid of the idea of a prescriptive hard boundary and to declare that a prefix now had to have a length carried with it. All of that had to be done across a period of 5 or 6 years, and it worked. It worked, and it bought us more time at the cost of process, and at the cost of justify your needs, and at the cost of a distributed activity to make it fly, but it bought time. And 2010 is when we arrive at the door of it bought time, but nothing lasts forever.
Well, yeah, you're right. Mate, across that period, 95 to around 2010, we were doing pretty severe conservation. Whereas before, the addressing czar was a couple of part-time people and a lot of faxes. All of a sudden, there were 30 or 40 people employed in this business, predominantly in the local registries. And if you sort of put the business together in finance terms, it was now a business worth a few tens of $millions a year, and the folk who owned networks were paying for it. No longer was this ARPA's largesse. So the industry kind of accommodated the fact that getting addresses had more process, had more people, there was more involved. But nevertheless, we all knew it was going to run out.
Yeah.
And with mobile phones, we all knew it was going to run out even sooner than we thought it was going to run out, even when we knew it was going to run out. The first time we looked at the sort of the result of conservation, we thought we had about 30-odd years. But like I said, the Apple iPhone was too popular. Everyone else started doing it too. Everyone thought we needed to have a unique IP address for every phone. Oops. We were making 1 billion phones a year even then.
Yeah.
It was never going to happen.
So part of the secret of prolonging the addresses, as well as shifting the boundary of where we considered a network and a host part, there's this other story lurking out there, yet another 3-letter acronym, Geoff. The emerging reality of how about if we change the address in the packet in flight so we can avoid this problem?
Network address translation, yes. And again, the IETF, which at the time had been earlier battling against the phone companies, and the IETF had a pretty consistent view of the world, managed to bifurcate internally. There were those folk who thought that changing addresses on the fly was worse than a sin. It was heresy. It was just anti-end-to-end, anti-everything. The whole simple, scalable model of the internet was that hosts had addresses. Don't touch them. Everything is address-based. This is how it scales. Leave it alone. But we didn't have enough addresses. And IPv6 was taking time. And so along came network address translation.
Yeah.
And some folk mumbling in corridors. And in fact, the IETF was unable to standardize it.
Yeah.
The various vendors.
Because of community pushback from people saying that they were philosophically opposed to a mechanistic model that got rid of some essential qualities about what goes into a packet and what you receive at the other end. The idea of people along the way changing the contents of the packet
is heretical.
Felt like anathema to some people.
Well, let's name them. You know who you are, Keith Moore.
There were more than... Yeah.
No, he's standing up in front of the IETF, and the basic catch cry was Nats are evil. Yes, we really did have a divided community. So 2008 was kind of an interesting year because at that time, someone looked back at the addressing plan and said, hang on a second. We have 268 million addresses reserved for future use. And IPv4 has no future. We're heading to the cliff. We're stuffed. What are we hanging on to them for? Let's just release them.
Yeah.
It'll stave off the problem for, a period of time. Let's do it.
So easy to say. I mean, deliciously easy to say. But I kind of have a feeling, based on my memory of the times, that there's this wonderful quality to what actually goes on inside the machinery of an operating system that has to come to the table.
And someone found in the Unix sort of code, and in fact it was IP.C, the original code I think that came out of the BSD contract. This is the implementation of TCP/IP. What it had in the processing part of a packet was that if the high order bits were all ones, i.e. 240/4, stop, throw it away, and report no.
Yeah, it's basically 3 lines in the C programming language that expands out to probably about 15 instructions in the kernel, the operating system, of almost every machine that inherited a network stack from this family had a rule that said, you can send packets, but you can't send packets with these addresses, because they were marked back in the 1990s as experimental, not for use. Future use.
Right. And the thing is, the BSD implementation of TCP/IP was done under contract to DARPA and distributed free of charge. So literally everybody, router vendors, anything that talked TCP/IP had the code base from that BSD implementation. And so when it said, nah, Class E, this top end is bad, then everything that talked IP was going, nah, it's bad. So this then brought out a delicious problem, because by 2008, we were staring at the cliff. We really were. It's kind of, oh my God. And partly it was, if we thought we were going to implement V6 before we ran into the wall, time is now measured in months, not years. This stuff is getting frighteningly close. And we were screaming at the mobile industry, but screaming at most of the growing internet, going, you're not doing anything in V6. We couldn't even see V6 on the network. You need to get moving. Now, the vendors of host software, be it Windows, be it Macs, which was actually just FreeBSD at the time, and being, various flavors of Unix, had done the work. Most of them had implemented the Kame implementation of IPv6 or had done their own. So there was V6 in the end devices, but the rest of the network, not so. So there still needed to be a lot of effort to make V6 actually happen. And it was an interesting debate. Should we spend a small amount of the remaining time available to the community to change, it was quite a large internet by 2008, to change the entire infrastructure base of the internet, ferret out all those remaining bits that say this address is bad, reboot them, reprogram them, change them over to go, oh yeah, I can handle this. A lot of effort, a lot of stuff even then in dusty cabinets, an indeterminate amount of work, and certainly because everyone was not accepting it, a not inconsiderable amount of work, and no one was going to pay you. No one was going to pay you. But we get back 268 million addresses. Yay! On the other hand, we could just ignore it and press on with V6. Because let's do one more stat. One more stat. How many addresses did we consume in 2008? Around about 150 million. And so by the time we were heading into 2010, our consumption rate really said, this is the end. And
how much time are we really going to buy by making sufficient investment to make it possible to use these addresses at the rate of consumption? The answer is 18 months to 2 years maximum.
No, George, you're an optimist. By 2010, 9 months.
So there's a parallel thing here, which I wouldn't identify the person, but it was a senior network engineer working in a large US telco who actually said to me, I was presenting a massive logistical nightmare to him, offering a way to extend the life of V4. He said, my supply chain logistics to do code work in the customer premises equipment, CPE, means I can put at most one patch in a year because nobody is prepared to test radical change. And they're just not willing to take 2 significant patches into field deployment for our customer base in 1 year. So you say I should modify things to extend the life of V4. I have to patch these devices. That means I can't get them to do V6. If you ask me to do this, I cannot do V6 work.
Right.
Contrary-wise, if you want me to do V6, I cannot do customer deployment of the change to modify 4 lines of C to make this network work, because nobody in my approval chain is going to let me do that in the same year. It's one or the other.
And it's not just that network provider's equipment. It's equipment everywhere. And it's stuff that I own that I wouldn't have a clue how to program. I just bought this, cute little thing from the local corner store. It was everywhere. So this was unrealistic.
Yeah.
Completely unrealistic. And so in recognition of that, the good folk at APNIC, you, George, me, Geoff, and our boss, Paul Wilson at the time, wrote this thing called Draft Wilson Class E.
Very small committee, Geoff, 3 people. Small committees can be quite effective.
Oh, small committees make brilliant outcomes. Yeah, right. And what this said was actually, it's your network, it's your rules, it's your devices. If you feel you can use it in a private context, knock yourself out. It's a bit like Network 10. If you want something internal where you control all the devices in the network. If you think you can use it, go and use it. It's no skin off anyone else's nose. Go and use it in a private context, and maybe that's a good thing, Don't use it in the public network. We could never make it work. That was the conclusion from Draft Wilson Class E.
Yeah.
There was another draft. Vince Fuller was working for Cisco, and he did a draft, Fuller 240 space, which was kind of different. He actually looked at the source code from the BSD TCP stack and said, it's here, it's there, it's there. It's actually a big problem, but we're a big company. This is Cisco. Let's just make it usable. Let's just declare it part of the IPv4 unicast address space and press on. Now, a little bit of discussion, a little bit of, should we, shouldn't we, either A or B. And then, like all of these discussions that don't really have a definitive way of solving it, we moved on. Because by 2010, smack, we were busy hitting the wall, and all the fun and excitement was, watching the last V4 address leave IANA.
Solving problems that were going to fix something in 2012 was actually a little far off for a process in registry that had to work out a fair distribution model for the parts of address we knew would work. That was in some ways investing time in work that didn't help our members or community. And there was a quality in that draft that, in a sense, was trying to get rid of an anomaly in a registry, because the line in IANA's registry that said reserved kind of stood out as a statement that made people think, what if? And that document we wrote didn't really say you're going to wind up using this and it's going to solve the problems of the world, malaria, cancer, and hunger. It said, can we not mark it reserved and mark it into a state where people can use it, but here's the rider around what we think use is going to look like. It's just really hard.
Use it in the privacy of your network.
Yeah.
Don't take it out for a walk.
We actually had signals from some providers, people like Amazon, who said, well, we can't guarantee every single host in our network can use it, but we have successfully deployed this as the switching fabric in huge data centers.
You're kind of jumping the gun. Because in some ways, a number of things happened between then and where we are now. And one of the issues about running out of addresses is that it wasn't a case of freeze, nobody move. It is where it is. If you've got addresses, lucky you. If you've got none, well, I'm sorry, you lose. There was this aftermarket of trading that if I didn't really need them or I had alternative ways of doing it, I was maybe doing some V6, whatever, and other folk were desperate, people started trading addresses. And it was still is a very, very contentious topic in address policy circles. But it's a pragmatic answer, of going, if there is need and there is folk with supply, supply will meet demand, off we go. It will equilibrate in trading. The implication, though, is that addresses now have value. And the market value started at around $10 an address and started to move upwards. Went up as high as $60, $70 an address. I think there were some deals that went even higher. But let's go back to those 268 million. At $40 an address, that's $1 billion worth of address. That's not an inconsiderable sum.
No, that is an awful lot of value in the world to quietly say we have no idea what to do with.
Exactly. Money had entered the room, and all of a sudden, here's this large pool of addresses equals large pool of money.
Yeah.
And, folks started getting ideas about, maybe we can monetize it.
Folk here means not you and not me.
Not me.
And not the
not
registries,
me.
Because our role in this is not to make money and put value into the world in that sense. That's not our game. We were never going to be there. Other people were looking at this going, how can we make this value?
Addresses are everybody's. They're not the property of the RIRs. It's a big conversation. But nevertheless, I'm kind of pointing out that the motives around this conversation, because it wasn't to stave off exhaustion.
No.
Now had this overlay of, it's not trillions of dollars, but it's, not 3 cents either.
Yeah. It's in the difficult area where even at the face of someone saying this is going to be incredibly hard, it's not impossible. Somebody would put time, effort and money on the table to liberate this resource and try to make it work.
Well, if it's under $1 billion of hard, then it's net positive in the long run. Okay. So this conversation about future's over, it's here, it's now, let's try and use it, keeps on resurfacing.
Yep.
And folk occasionally have stood up something using a 240/4 address and done some experiments.
Yep.
And one of the early ones, it was a couple of years ago, was actually using the RIPE Atlas in 2022.
Yep.
Where they did a little hack on the Atlas code and said, let's have a look at trace routes that are recorded by Atlas, and let's see if there were any intermediate hops that use addresses in 240/4.
So you're going between two addresses in the general globally routable pool, and you're using the facility that shows you the stages along the way that actively engage in passing the packets. If any of them show a 240/4, somebody's deployed it in infrastructure mode inside their network.
Right. If you're using network 10, the trace route will show that some of the intermediate hops came from a router using network 10. If you're using 240/4, then some of the intermediate hops will show there's a network interface using 240/4. They looked at all these trace routes they'd collected and, up popped Amazon AWS using it internally.
Right.
Nothing wrong with that.
Right.
Nothing wrong with that.
That's the thing I was alluding to earlier, a little ahead of myself. Evidence emerged, people were actually using it.
People were using it. So then they decided to go one step further, because you always can, right? And so they set up a server with that address and set it up on a friendly site that had access to the interdomain routing space, advertised a route, and said to all the Atlas probes spread all over the network, go trace route to that address. Now, they tried it across 76,000 probes all over the net, and what they actually reported was that 34 probes actually got there.
34 out of
7,600. It's not a big number.
Yeah, but some did.
Yeah. They're all hosted in Verizon Business, AS701. So, it was a funny
network operator had both network routing filters and no technology barriers, and the sites of the Atlas probes were not behind a machine that was going to exclude these. It is actually possible to state it could work, but we're talking below 1%.
One network, yeah, right. I did it again because there's now been a test server stood up in the Czech Republic, also advertising an address, 242. And I did 190 probes in Atlas, not 7,600. One.
Yeah.
One. And I'm in the Czech Republic, not in Verizon, not in America, only one. And I thought, okay, maybe 190 is not enough. Let's turn up the wick. 1,000 Atlas hosts. How many did I do? 0. Oh.
Doesn't completely align with the previous number you were getting.
Right. There's a lot of blocking. But let's go further, because this is now becoming a measurement trail. Let's go down the measurement trail. Atlas has 12,500 probes. They're spread across a lot of places, but it's only 12,500. We have talked about APNIC's measurement program. And although Atlas is astonishingly flexible, APNIC is astonishingly inflexible, but it's bloody big. We do around 25 million ad impressions a day. 25 million different hosts participate in the measurement system.
Yeah.
So we're not talking a few thousand.
No. And these are devices behind NATs, devices in the home, devices on mobile, devices in Wi-Fi networks, devices everywhere. So it's not probes that have been carefully, lovingly placed by network engineers. This is real end user lived experience.
This is the gory internet.
Yep.
And so what we do, because all you can do really in an ad is say, go fetch this web object. Go fetch. So the web object, in this case, is sitting behind a 240 address. And so you can only fetch it if everything works in your favor. The wind's downhill, all that kind of good stuff. if nothing works, then you're not going to get there. And many things can go wrong. Routers reject routes with a destination of 240/4 because you can hardly see it in any of the route collectors. The configuration commands for the routing system might reject it.
Yeah.
Almost anything in V4 is behind the NAT, and it's behind actually customer premises equipment. And it's entirely likely the NAT goes, I'm not going to translate to a destination in 240/4 because that's obviously a scammer. I'm not going there.
Yeah.
That's a bad address. Drop the packet.
Or
mobile networks.
My code base is inherited from that DARPA contract 3 decades ago, and it has 4 lines of C that say, if the top bits are set, don't do it.
Well, I only paid $10 for the CPE. I'm not paying for an awful lot of software engineering. It probably was that code. So there's an awful lot of reasons why, things won't work. But anyway, let's try it. So we set this up late July, early August, and ran it. We did 130 million tests, and each of them unique. So a lot of testing. How many hits? Well, it was more than 35. Yay. It was 58,914.
How did they distribute?
Oh, well, that's the next thing. I was just going to go, well, that's not just 1%. It's less than that.
Yeah.
It's not 0.1%. In fact, it's 0.04%. So it's tiny.
So in absolute number terms, it is a tiny cohort in the surface of the real global lived experience internet you and I and everyone else loves. A tiny percentage can do it right now.
Right. And this network that hosts the server is hosted in the Czech Republic, or Czechia, depending on what your flavor is and which name you like. And it's pretty well connected. It has quite a number of peering neighbors where it is announcing that route. If I look at RIPE's RIS on this particular network, I think it has around 788 peers for this network. So a lot of people locally in the Czech, Slovakia, Romania, Russia area have a direct link to this network.
Yeah.
Partially through the switching infrastructure of DE kicks and otherwise through other forms of direct peering one way or another. So a lot of folk get to pick it up. But we only see hits really in volume from Romania and the Czech Republic. That's all. Tiny amount from America, some from the Russian Federation, not a lot, and that's about it. So the ad network has a bit better visibility than just countries. I can tell which network you're in because you have an IP address that's being announced into the routing system, And there's actually this odd kind of functionality. Either you don't see it at all. And that's fine. Most networks out of the 75,000 networks out there on the internet, all bar less than 100 can't get there. Of those ones that can, and they are in the Czech Republic or Romania, a small number of them, and they're quite big, almost 80% of all of our tests are successful. AS 9050, which is RTD in Bucharest, it's a big network. You can get there. Quantcom in the Czech Republic, NG Intersat in Romania, 86%. So a bunch of networks go, every host can get there.
So this kind of goes to an interesting place for me, because what it says is if you have predominantly newer equipment and if you had a willingness in your network administration to invest time and effort to make this work, this isn't an absolutist, it simply cannot work no matter what you do world. You can make this technology work. And so if I posit someone advocating for a change in our process to recognize this as a valid network, and there are people doing this, and they're doing it of good intent, I can't stand up and say in a forum, no, I'm sorry, what you're saying simply cannot be. It disobeys the laws of physics. This isn't a law of physics problem. It's possible to make this work.
Well, I think you've leapt too far, because I said some of them have hit rates of up around 90%. Means every host in their network, it all kind of works. But a number of others in the same geography, like AS 48161, which is called NGAS, whoever they are, again in Romania, only 30%. Only 30. What happened to the other 70%? If it's not the end systems, and it's not the network, because they get the route, because 30% reach it, but the other 70% can't. And I'm leaning, don't know why, but I'm leaning towards NATs and CPE, consumer premise equipment, that some network providers are fully mobile. They have complete control of the user experience. Some are wired networks where the user, the customer in the house, has bought their own equipment to interface to the network, and nobody controls it except you and, the vendor who sold you that $10 thing, who no one claims responsibility for. And maybe the 30% is because of this thing about consumer premises equipment.
Right. So this in some ways is a reprise of what we saw with deployment of IPv6 in Reliance Jio in India. Handsets, mobile devices, Android, Apple, it is a centrally managed distribution. If the people behind Android decide to make it possible to do V6 or Class C networks, within a year, virtually every one of the handsets deployed in this community of mobile users have that capability. But a CPE is slightly different. I'm currently running my 4th or 5th CPE over the last 30 years. I tend to view them as a minimum 5-year purchase, and I hope to get more like 10 years. And the problem with the CPE is you get 2 years of software upgrade if you're lucky, and after that, what it does is what it does. That's it.
I'm sorry, you upgrade your CPE, do you?
Well,
no one else does. There are two kinds of wired networks out there. There are ones where this equipment is owned and operated by the service provider, and they tend to do a decent job of tracking down bugs, keeping it up to date, and having some uniformity of behavior. But they're a rarity because it costs. Other providers simply go, here's a list of devices that'll probably work. Knock yourself out. It's your problem. Go down to your local corner shop that sells electronics, go to Amazon, whatever you want to do, go and buy something. Not our problem. And it's those ones which are the real sort of leap into the unknown. And do they accept 240 addresses? I don't know. You don't know. Nobody knows. And so for those folk, which is certainly even in these geographic areas where the route is being carried by the network, that equipment says, I can't get there. And it's kind of difficult to fix that because there's no centralized fix anymore. You're off in a very, very bleak area. And why should that customer go through hoops and contortions for no direct benefit? It's not as if Google's using 240 addresses. It's not as if their internet will magically change for the better. There's no motivation to do it. So I would take the view, George, that figure is no glimmer of hope. The door is still slammed shut. We can't make it work.
So if we consider Sky in the UK and their decision to deploy IPv6, Sky as a network didn't allow customers to just randomly buy a router and bang it on the network. You ran Sky's router. And Sky knew the software version of every single router in the UK national deployment. It still took them somewhere between 18 months and 2 years to very, very carefully, for about 5 versions of router software, deploy the changes to turn IPv6 on in their national network. And it only worked because they required you to run their CPE. If you live in any economy where you can bring your own CPE to the table, the likelihood of successfully deploying this change in network technology is pretty well close to zero.
Exactly. And this is the problem. Because I also say, Sky probably spent a lot of money.
There had to be an upside benefit for them in choosing to do this.
They thought customers would value that kind of managed service, and likely some did in their market, and that's fine. But, it's not everyone that does that. Some just simply say, go to the corner store, get what you want, it's not our problem. We just deliver the packets to the front of the door. Whatever you're doing in your CPE is your problem. Good luck. Bye.
So there's kind of a moment in this where, because we work in the registry, And people in the wider community in IETF are submitting drafts that, unlike the proposal we floated, which was the private use proposal, are putting forward an idea, can we make this globally routable? Where I think you and I might have some mind share is that we're looking at this doing, there's something like the Hippocratic Oath here. First, do no harm. If you put a label on these addresses saying they're globally routable, what is the potential for this to go into some very strange places? And it's looking like it's more likely for most use this is damaged network, not viable, globally routable network.
Well, take the example that we're using as a test point. I bring up my web service. I get a 240 address. I stand it up, outside in the closest area of network. Evidently, the route will propagate, a tiny amount of space. In the Czech Republic, which is well connected east and west, 0.04% of users actually see it. So you've done everything right. You're just using the wrong address.
Yeah.
It's tainted. It's not useful. And so I'll go back to the original advice in that draft Wilson thing that said, it's an address, that's fine, but it's not the same as all the rest. It's got a history, and that history is unbelievably expensive to erase.
Yep. The supply chain logistics of fixing this problem go beyond the level of effort that returns on the investment to get there.
And no one's come along. No internet trillionaire has appeared. So I'll pay for everything.
Yeah.
Just send me the bill. Ha, I wish. So there's no one to pay for it. It's just
the people
pain.
with that kind of money would rather go to Mars than invest in fixing this problem.
Well, if you're going to get personal, yes, they do. And yes, that's the issue. And just for a mere 268 million IPv4 addresses, the answer is you're joking. So that advice originally was it's unusable. Just use it privately.
Yeah.
If you control everything, knock yourself out. It's your problem. Just don't take it out for a walk on the street. That would be dangerous.
Yeah, I think this is one of those measurement activities done in the ad network, Geoff, which actually does go to informing a public policy debate, because this is a real question. And putting on the table, I tried and this is what I saw, that's actually a substantive contribution.
I think so too. I think it's, good policy really relies on good data, and good data relies on, a sensible and well-constructed way of understanding what you're looking at and what do we see. And so this has certainly been an example of doing that. So I'm quite happy with this work. It didn't come up with the desired answer. Yes, it's usable. Let's go and monetize these addresses.
Well,
absolutely not. But I think you're saying the Hippocratic Oath, this is the way that minimizes the harm to anyone who thinks they can use it, and to everyone else who might be forced to use it and suffer the, it doesn't work kind of problems, which is just painful, difficult, and should be avoided.
Yeah, and people can read about this on the APNIC blog or on the lab's blog site, can't they? You've published this.
Absolutely. I've published the work at the start of the week in September 2024. I don't think anything's going to change very soon. Over the next few years, this is still probably a relevant answer because, when you and I buy CPE, that device has to work for years. I paid $50 good for that, so I expect 10 years of life out of it. So, nothing will change.
Ain't changing it anytime soon. Thanks, Geoff. That's been fascinating.
Thanks, George. See you next time.
If you've got a story or research to share here on Ping, why not get in contact by email to ping@apnic.net or via the APNIC social media channels. Also, remember, the measurement@apnic.net mailing list on Orbit is there to discuss and share relevant collaborative opportunities, grants and funding opportunities, jobs and graduate placings, or to seek feedback from the community on your own measurement projects. Be sure to check out the APNIC website for all your resource and community needs. Until next time.